All right, so what if instead we have a spring, right? If I put something on the end of a spring, it's going to kind of bounce back and forth, wow, 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 nice way. And we can think about that on our energy diagram, right? If we start an object at one end of a stretched spring, right? Well, what's going to happen? It's going to be all potential energy. Now, in this case, it's spring potential rather than gravitational potential. As I let it go, that potential energy is going to decrease. It's going to kind of fall down the potential energy hill, and it's going to gain some kinetic energy. And how much kinetic energy is it going to gain? Again, I can kind of read that off from that total energy minus potential energy area. And now it's going to kind of in the middle hit that maximum velocity, that maximum kinetic energy, and then it's going to kind of start to come back up the other side of the hill. And hopefully you can see that once it does so, it's going to like stop here and then come back and just kind of spring back and forth forever in this little parabolic energy well. So here's a little bit more of a general energy diagram. So here's a question for you. If I release it from rest at point x1, where is the maximum value of position that it will reach? Where would it have zero kinetic energy, and where would it have maximum kinetic energy? Well, hopefully it's clear from number one that it'll reach, if it starts out with all potential and no kinetic, that it will, come back and it will stop here when it's out of kinetic energy again. So it'll reach up to x5. It'll also have zero kinetic energy only at x5. And its maximum kinetic energy will be here at x4. Excellent. All right, so what happens if I do something different? What if I kind of put my object here at x2, and we're going to start it at rest again, and I just let it go? Well, think about what would happen to a skater if I did that, right? I can come here to my skater. Please excuse the interruption there. What happens if I come to my skate park, right? Let's try that with my skater, and I'm just going to put my skater right here. And ready? Well, doesn't really go anywhere. And even if I displace the skater just a little bit from that point, they don't get to leave. They just kind of bounce back and forth. This is what is referred to as a stable equilibrium. An equilibrium is a point for which small disturbances cause you to just oscillate around, but you don't get to leave. So this is a stable equilibrium. If I put an object here, it's going to stay there. And even if it gets wobbled a little bit or pushed in the wind, or I don't quite start it at rest, it's not going to leave. It's just going to kind of stay in place. So this is a little cup, it's a little stable equilibrium. What if instead I started at rest at x3? So I'm going to balance it. Again, we're going to balance it perfectly carefully, the skater or whatever, with velocity equals to 0 right on top of that hill. Well, in theory, it shouldn't go anywhere. The top of the hill is flat, and my skater should stay perfectly still. But even the tiniest little nudge one way or the other, if I don't release it totally at rest, or if it gets nudged just a little bit, it's not going to kind of come back to where it started. Instead, our skater, let's be very careful here, ready? Oh, I wasn't careful enough. No, I still wasn't careful enough. I really can't get an accurate, I can't really quite get it to be stable right there. So it is an equilibrium, but if I nudge it, it'll kind of fly off in one direction or the other. So this is what we call an unstable equilibrium. And you might notice, of course, that our stable equilibria are concave up and our unstable equilibria are concave down. All right. Because obviously if I nudge it this way, it'll kind of go over here. And if I nudge it this way, it'll go over here. Well, here's a little sample. This is actually a sample AP problem. So here's a graph above that represents the potential energy U as a function of position, okay? If I release the particle from rest at position R0, okay, so I'm gonna, and again, what's my advice? Always make that horizontal line for total energy, and I happen to know that it's at 0 velocity. What will its speed be at position 3R0? Okay, well, if I come over to 3R0, I know that I started off with 3U0 of energy. Now I only have 2U0 of potential energy. So I can look at that gap and say, oh, well, my kinetic energy there needs to be, well, 3 minus 2 is just 1U0. And then I can plug that into 1/2 mv squared. So I'll get what for v? I'll get root 2u0 over m, I guess, for that. So I can look at these kinds of diagrams and pull useful information out of them for that. So you can actually get a little bit more useful information off of these. It turns out that you can actually know the force from your graph. And it turns out that the force is going to be the negative derivative of your graph. Let's just, before we say why this works, let's just check to make sure it does. So if I take my red ball here, okay, my derivative here is already negative. It's a negative slope. So that tells me that my force should be positive. Well, that makes sense, because what's my red ball going to do? It's going to move in the positive direction. It's going to want to roll downhill. It's going to want to go in the positive direction. So that works. Here at x1, my slope is positive. So that means my force should be negative, which makes sense because my object's going to want to move in the negative direction. And here at x2, my slope is 0. It's because it's at a minimum. So my force should be 0, which makes sense. At x2, my ball shouldn't move at all. Why does this work? Well, why does this work? Well, it works because you might recall that the integral of force over distance is work, which is change in kinetic energy, right? Well, if my kinetic energy is going up, right? If my work is increasing my kinetic energy, it is probably decreasing my potential energy, right? So I can write here negative change in U. And if I go ahead and take a derivative of both sides to get rid of this integral sign, I can get f equals, or I guess if I write this maybe in differential form, it's kind of the same thing. I'm going to get f equals negative du over dx. So I take it, this is really just saying that if I'm doing work on an object and the kinetic energy is going up, that energy is coming from somewhere, and my potential energy is going down. So f equals negative du dx. And this is an important equation. It doesn't come up that much, but it will come up at least once on your exam. And the important thing is, this is one of the first important equations that we get that is not on your formula sheet. I mean, I guess this one is, the work equation, but f equals negative du dx is nowhere on your equation sheet. All right, let's talk about let's get to some examples real quick in our last couple minutes. So here is the energy, just to note, you can also show whether forces are attractive or repulsive. So if this is the molecular bonds, this is the energy for the molecule of hydrogen chloride. As the two things get closer or further apart. If they try to get too close together, you can kind of see that our force is going to push them apart. If they try to get too far apart, you can kind of see that it's going to pull them together. So for small distances, the force is repulsive. For bigger distances, the force is attractive. All right, and now we'll do some worked examples.